Section 2.2, we're going to talk about the inverse of a matrix, which is a highly applicable topic that comes up in a lot of future sections, but also just future courses. And we're going to start by sort of relating it back to something we're familiar with, which is the inverse of real numbers. So even if you're not necessarily familiar with this right off the bat, I think you really are. And so every non-zero real number, n, has an inverse, a multiplicative inverse, which we call 1 over n, or n to the minus 1. And that means that they're inverses because when you multiply n and n inverse, you get the number 1. Right? So that's what it means to be a multiplicative inverse. So for example, we know that 2 and 1/2 are inverses of each other. Right? So n is 2, 1 over n would be 1/2. And we know they're inverses because when you multiply those two things, you get the number 1. Now, this is, the way we typically think about multiplicative inverses. But the way I'd like to rephrase this is instead of writing 1/2 as 1 divided by 2, we can instead write 1/2 as 2 to the minus 1. Right? And in this light, when we kind of look at it like this, it becomes an exponent problem where we have like bases with different powers. We add those powers, and so we get 2 to the 1 minus 1, or 2 to the 0, which is 1. And so this is really the way we want to be thinking about this multiplicative inverse, where you have a number raised to the power of 1, and that means its multiplicative inverse is going to be the same number raised to the power of minus 1. Okay? And they're inverses because when we multiply them together, we get the number 1. And this is true for any real number. Now, this is the same thing with matrices, except we're not thinking about numbers, right? Matrices can't be written as fractions like this. They can only be written in with this sort of -1 power kind of thing. Now the difference is, every number has an inverse, a multiplicative inverse like this. However, only some matrices are going to have that multiplicative inverse. And so for one thing, in order to talk about the multiplicative inverse to begin with, we need to talk about a square matrix. Okay, so we need to have a square matrix to even consider having an inverse, and even then, sometimes they won't be invertible. But anyway, if we do have a square matrix and it turns out it is invertible, then we denote that with the same kind of notation, right? A to the minus 1, the same kind of notation that we just used with the 2 for a second ago. And we say that it has the following property. This is the property of two matrices being each other's inverse. That when you can multiply the two things together in either order, you get I. And I, what's going on here, this is I sub n, depends on the size of the matrix that we have. And I sub n was something we mentioned a couple times before, most recently in the last section. I sub n is the n by n identity matrix. So we have seen this in a couple previous sections, again, right in the last section, for example. But just as a quick reminder, the identity matrix is the matrix that has 1s going down the diagonal, however big it happens to be, and then just 0s above and below the diagonal. Okay, and so this is like the matrix version of the number 1 is the way we've kind of described it. And so a 2 by 2 would just have 2 rows and 2 columns, right? We can have any sized identity matrix. And notice that, just thinking about the last section, you're multiplying two matrices here, and we're allowed to do that in this case because we do have that square matrix, right? So A and A inverse are both going to be n by n, which allows us to actually multiply them because those inner dimensions match, right? So just kind of linking it to some of the material from the last section. Again, though, just to kind of summarize, a matrix may or may not be invertible. It needs to be square, and even then it may not have an inverse. And we say if it does have an inverse, then this property holds, right? It's the same kind of idea as multiplying 2 and 2 to the minus 1. You get the number 1, that makes them inverses. When you multiply the 2, you get the identity matrix, that makes them inverses. All right, cool. Just a couple vocab words here. So if a matrix is invertible, another way to say that is non-singular. And so you'll see math textbooks and future courses potentially use that word. I usually just say invertible or non-invertible. And we say it's not invertible if it's singular. Just some vocab just to be aware of. Again, future courses, future classes, textbooks, things like that. You just want to be able to identify what those different words mean. So let's go ahead and show these two matrices right here are each other's inverse. So they're both 2 by 2. Let's call this one matrix A. We'll call this one matrix B. What we're going to do is we're going to multiply A times B on the left. We'll also do it on the right. And in both cases, we'll see that we get the identity matrix. Let me just also sort of bring that back from last section. Multiplying on the left, see how the inverse is on the left here? That's different than multiplying on the right, which is what the second one's showing. And so we'll show it in both directions here. And again, thinking back to the last section, those two things are not always equal. All right, so let's first multiply A times B. So remember, we make this table, and we put the matrix on the left down at the bottom here. And then we put the one on the right on the top. And we know that we're multiplying a 2 by 2 and a 2 by 2, and so we're going to end up with a 2 by 2 inside here. And as a way to remember how to do this, you know, this entry right here lines up with this column and this row, and so we multiply that column by that row in order to get this entry. And then we slide over and we do this column and that row, right? So when you set it up in this table form from last section, it makes it nice and easy to do. I'll write the details out in this one. So in this one, you get minus 5 times minus 1, so 5. And then minus 3 times 4/3 is minus 4. Over here, you'll have 5 times minus 1 again, and then 5/3 times 3, so it'll be minus 5. Over here, you'll end up with minus 4 plus 4, and over here, you'll get minus 4 plus 5. So I know this is just in the last section, but, you know, look back at those notes if you need to remind yourself how to multiply matrices, but notice what happens here is this simplifies down into 1, 0, 0, 1, which is the 2 by 2 identity matrix, which is exactly what we were expecting, right? If these two things are inverses, we should be able to multiply them and get the identity matrix, and so far we've shown that we multiply A times B, we get that. When I'm doing this in class, in person, I then ask people to try this one themselves, just to practice multiplying matrices. Multiplying matrices is the kind of thing that you need to know how to do kind of quickly. Like, it doesn't need to be like super quick, but you know, multiplying matrices is usually like within another problem rather than a problem in itself, and so we do need to know how to do this somewhat quickly, right? So again, I would recommend maybe pausing the video and just reminding yourself how to do this, give it a try, and when you're done, go ahead and unpause it, and I'm going to go over it right now. So I'll write the details out again. This first entry ends up being 5 minus 4. This entry is 3 minus 3. We get minus 20/3 plus 20/3 in that entry, and then we get minus 4 plus 5 over here. And the cool thing is, we once again get the identity matrix when we simplify that down. And so we showed the property holds here, right? We multiplied the two matrices in both orders, A times B and B times A, and we got the identity matrix in both cases, and so that means they are each other's inverse. So I'm just going to write that down. So since A times B was the same thing as B times A, and in both cases we got the 2 by 2 identity matrix, that means A and B are each other's inverse. All right. So how do we actually find these things, right? And what can we do with them? That's what we should be really asking ourselves. We've kind of introduced what the concept is, what makes it something an inverse with another, some matrix with an inverse, and the next couple pages are about finding them and then using them. So let's do that. So Theorem 4 tells us how to find the inverse of specifically size 2 by 2 matrices, right? So let A be A, B, C, D, and so let me just write this down just so we're clear about this. This is how we can find the inverse specifically of a 2 by 2 matrix. There's a very easy formula to do that, and we'll see a general formula that'll work on any matrix on the next section or the next page. But if we have a 2 by 2, so it looks like this, A, B, C, D, and assuming that AD minus BC is not 0, then it means that A is invertible, and the inverse is given by this formula right here. So notice what happens here. You used to have A, B, C, D. Now it's D, negative B, negative C, A, right? So A and D switch places, and then B and C get multiplied by negative 1. And then this part right here, the 1 over AD minus BC, this is what's known as the determinant. Right? You can see me defining it down here. DETA stands for the determinant of A. And it's not something we've learned about yet. We're going to learn more about that in section 3.1, but I just want to precursor that here and just say that that's not just some meaningless statement. That's called the determinant. And the idea is, see how it's in the bottom of a fraction here? The idea is if that ends up being 0, well, then you have 1 over 0, and that's not okay. And so that's an indication that A would not be invertible. Okay? So it's a nice, easy formula to use, again, for a 2 by 2 specifically. And so let's use it on the thing we just learned. Let's find the inverse of this matrix A from the previous problem, this 5 minus 3, 4, 3, and we'll show we actually get this matrix B that we just previously proved are each other's inverse. So I'm going to do it right here. Try to write a little bit small here because we're going to fit it on 2 lines. So we're going to do the inverse of that matrix up there. 5 minus 3, 4, 3. And I'm going to use the formula right here. So you do 1 over AD minus BC. So that's going to be minus 5 times 3, minus 4 times minus 3. And then you're multiplying that times the matrix where things sort of switch spots or get multiplied by negative 1. So the A and the D switch spots. That becomes this. And then the B and the C get multiplied by negative 1. So that becomes this. Okay? So what you're doing is you're multiplying this kind of jumbled matrix by this fraction. And we learned in the last section, when you multiply a constant by a matrix, it just, each entry gets multiplied by that number, right? And so this really ends up being minus 1/3 times that matrix, 3, 3, minus 4, minus 5. And then each one of these terms just gets multiplied by minus 1/3. And so we get minus 1, minus 1, 4/3, 5/3, which is exactly the matrix up here. Right? So you get this matrix by using this formula, and we see that we did get the exact same matrix as above. But I do just want to emphasize again, this is specifically for a 2 by 2. Right? So it's only going to work for a small subclass of matrices. But if you do have a 2 by 2, it's a nice, easy way to get that. Just remembered I needed my graphing calculator, so I'm going to pull that out and turn the page to the next one. I don't quite need a graphing calculator yet, but eventually we'll use that to help us find the inverse. Before we do that, let's talk about one way that we can use it. So, gosh, I feel like I keep changing this typo up here, and it keeps coming back. That should say AX equals B there. So anyway, the inverse, if A has an inverse, it gives us a way to solve this equation. And it's stated by this theorem, and I'll show you what this theorem is saying. So it says if A is invertible and it has to be square, that means for every B in Rn, then the equation AX equals B will have this solution, X equals A to the minus 1B, right? So if you have this equation and you want to solve it, which we're always trying to solve in this course, and just general applications of linear algebra are always trying to solve AX equals B. Well, this is the solution to that right here. You just multiply B by the inverse of A, right? That's what this is saying. And so let me show you why this is the case. We'll do kind of a little mini proof here. Let's suppose that A is a square matrix and it's invertible. And let's suppose we want to solve ax equals b. Right. Well, let's start with that equation. I'm just going to rewrite the equation right here. And, you know, we talked about in the last section how if these were numbers in here, you could just divide by a and to isolate the x. But since this is a matrix and these are vectors, you can't just divide by matrix, right? There's no such thing as matrix division. And so instead, what we can do is we can multiply on the left by the inverse. Right, so I just multiplied both sides of the equation by the inverse on the left. And the last page tells us that that thing just cancels out, right? So the last page is telling us that if we multiply a by the inverse, it should just cancel into the identity matrix. So I know that this is going to cancel, a inverse times a is going to cancel into the identity matrix, right? And so what we really get here is we get the identity matrix times x, and then we get just a inverse b on the right. And you know, as another reminder, the identity matrix is just the matrix version of the number 1. So when we multiply this vector times the identity matrix, it just stays the same. Right? This just equals x. And so what we just found is that x is a inverse b. Right? And x is going to be a vector of values, of solution values, x1 through xn, and so each entry is going to be shown by this product. Now, the thing I'd like to point out here is kind of an important thing, which is that we multiplied on the left by the inverse. Notice that, let me squeeze it in over here. If you tried to multiply the inverse on the right side of that equation, so if you did like ax, and then you multiplied on the right by the inverse, and then it equals b, and you multiply by on the right. Right, that's not going to make sense based on what we talked about in the last section, because x is n by 1, and so is b, but the inverse is square. And so the inner dimensions don't match if you try to multiply on the right, right? You're going to have 1 matching up with n, 1 matching up with n, and so it doesn't match. In other words, x times the inverse and b times the inverse don't exist. Right, so we did talk about that in the last section, how you can't just change the order of matrix multiplication. And so that's, you know, you can see it's important you're multiplying on the left here, because if you even tried to multiply on the right, the dimensions wouldn't match up, and you don't, not only do you not get the answer, but it's not even possible to do that multiplication. All right. So let's put this to practice. All right. We know if we have a linear system like this is in the form ax equals b, then we can just solve it by multiplying by the inverse. So let's do it right here. So I've got my sample system here. You know, this is just a linear system, and I want to just remind you that it looks like ax equals b in this kind of sense. A would be the coefficient matrix, x is the matrix of unknowns, or the vector of unknowns, and then b would be the constant matrix on the right. Right, we had some early homework and sections that talked about translating between systems and matrix equations. Right, so this linear system is really this matrix equation, and so we can just find the inverse of this matrix A, multiply on the left to solve it. And so let's find the inverse of this. We're going to use the formula on the last page. So we're going to do 1 over AD minus BC. So that's going to be 1 over minus 12. Switch the A and the D location. Make the other two multiplied by negative 1. And that's it. All right, just multiply the negative 12 through here. You got the inverse. So we'd get 1/2, 1/6, 1/4, negative 1/12. Right, this is the inverse. And so that was useful because we can just do what we just did up here to solve this equation, right? We can just take the inverse and multiply it on the left side of the equation, on both sides, of course. It's just going to cancel on the left, and then the right side is going to be the answer. And so that's the next step. We're going to multiply. I want to point out on the left again. It's got to be on the left side to solve the system. And so let me do that. All right, so we have, let's see here. I'm going to rewrite this equation. So this is my ax equals b again. Just trying to show the details here. We're going to multiply on the left by this inverse, and so we're going to do this. Right, so that looks like this then. And I should have left some more room here. Oops, let me slide this over. Because we've got to multiply on the left, right? I don't want to slip it on the right. That doesn't make sense. It's got to be on the left side of that vector. And then based on what we just showed above, these two things are just going to cancel right out. It's going to equal I2. And so we're just going to get x on the left, and then the product of those two things is the answer. Right? And so we're going to get this. And then when we do that multiplication, it ends up being this. 9 halves plus 3 sixths, 9 fourths plus minus 3 twelfths. And since you're multiplying by the identity matrix, this just stays the same. Excuse me. When you add these two things together, you get 5, 2. Right, so we're able to solve this system just by multiplying by the inverse. So it just gives us another tool to be able to solve systems. Sometimes multiplying by the inverse is quicker or faster, or maybe more effective. Versus row reduction or some other techniques. But the other thing is you need to have an inverse, and we don't always have an inverse, right? So we're only going to have an inverse for some matrices. All right, cool. So before we learn about how to find the matrix of any, the inverse of any matrix, because we've only talked about 2 by 2s, let's just throw a couple properties out there, a couple theorems, or a theorem with a couple parts to it. So the first one saying if we have an invertible matrix, then the inverse is also invertible, right? So in other words, if you inverse the inverse, you get back to the original, right? That's what this is saying. The inverse of the inverse is the original. No big deal there. That should make sense. If we have 2 invertible matrices, so if A and B are both already invertible, then their product is also invertible. And moreover, if we do the inverse of the product, it's the product of the inverse in reverse order. In other words, this, right? So if you multiply A times B, and then you want the inverse of that, it's the same thing as doing the inverse of B times the inverse of A. So notice how the B went in front and the A went second then, right? So this is kind of similar to what we saw in that last section. Right, when we had AB inside the transpose, that became B transpose A transpose. So it's kind of like that property, just with inverses instead of transposed. And then the last one's just saying that if we have an inverse and the transpose is also invertible, again, the transpose is from last section, and it turns out that the inverse of the transpose is the transpose of the inverse, right? So if you want to take the transpose and then invert it, well, you can just transpose the inverse. Just in case this is not clear, I know there's some ATs floating around there. AT is the transpose of of A, and in that, all rows of A become columns of the inverse of the transpose, excuse me. Alrighty. Let's find the inverse of any matrix, not just 2 by 2s. That's what's on the docket next. So this is how we find the inverse of any invertible matrix. Right? Not every matrix is invertible, but if we have an inverse, this is how we find it. As a quick reminder, this thing that we learned previously is just for 2x2s. This will work for any matrix, including 2x2s. Okay, so let's read what it says. A square matrix A is invertible if and only if, as a quick reminder, that means it works both ways. If and only if A is row equivalent to the I sub n, right? So that's the identity matrix. And moreover, in that case, the row operations that changes A into the identity matrix changes the identity matrix into the inverse. It's a very interesting thing there. So, in other words, this leads directly to this algorithm for finding it, right? So let me just say that one more time. The same row operations that row reduces A, so that row reduces A into the identity matrix, if you apply those same operations to the identity matrix, it changes the identity matrix into the inverse. That's pretty interesting. And so that gives us a method and a very clear, easy way to find the inverse, right? So algorithm for finding the inverse. Put A and the identity matrix into a matrix together, right? So this is those two things inside of a bigger matrix. Then row reduce A, right? Just do RREF. If it changes into identity matrix, right, then this will change into the identity matrix. That means that the identity matrix comes along for the ride and changes into the inverse. If A doesn't change into the identity matrix, it means that we don't have an inverse. Right, so let me just sort of say that again, and maybe I'll write it out in words as I explain here. What this is sort of telling us to do is it's telling us to put A and I into a matrix together, right? So they're inside a matrix. Use a calculator to do RREF. Right, you'll do this. If there's an inverse, A is going to switch into I. So it should be I. Now, since I is also in the matrix with A, it's also going to apply those row operations to I. And so then I will change into the inverse. Right, so you just row reduce it. You just literally just put it in your calculator like this, hit row reduce, and it'll spit out I and then the inverse. Now, since we know not all matrices have an inverse, if you put it in there with the identity matrix and you row reduce, and you get something that's not the identity matrix here, and really anything else here, right? This implies that there's no inverse. Okay? Really super easy to do. So there's two examples at the bottom of the page. Hopefully you can already tell that one of them is going to work, one of them is not going to work. I will go through the first one with some detail, and then I will trust that you know how to use the calculator to find the inverse on the second one. Let me know if you don't, though. So let's find the inverse of this matrix if it exists. So let's call this matrix A. So we're going to put A into a matrix with the identity matrix. Since it's a 3x3, we're going to use the 3x3 identity matrix. And so that looks like this. There's A. We're going to put it right into the identity matrix. Into there with the identity matrix, I mean. And what the theorem and the algorithm here say is that operations that change A into I also change I into the inverse. Right, like if you were going to row reduce this just by hand, you'd really be focusing on the matrix A, because you'd be trying to put a pivot here, you'd go down right, you'd be trying to put a pivot here, you'd go down right, you'd be trying to put a pivot here. Right, so none of those things have anything to do with the matrix on the right. And so when you focus on row reducing this, you're doing the same operations on those rows as well. And so it'll be transforming it without even thinking about it, really. In a calculator, just as a quick reminder, this is how that looks. So let me make sure you can see that okay. All right, let me do this from scratch here. Let's get as much on this. So we put the matrix in. So we go to the matrix button. I'm going to edit this matrix. Oops, I forgot to go to edit. Slide over to edit. I'm going to edit that matrix. How big do I want it to be? I want it to be 3 by 6. So it's going to be a 3 by 6. And I'm just going to punch in those numbers. So remember, you punch the number and then hit enter to go to the next one. So 1, 2, 3, and then we'd have 1, 0, 0. The second row is 2, 3, 4, 0, 1, 0. The third row is 4, 2, 1, 0, 0, 1. All right, so now that this augmented matrix is in there with A and I, and we just want to row reduce it, right? So the way you do that is you quit. I'm going to clear out the home screen. Okay, we want to go to matrix. We're going to row reduce. You go all the way to the bottom. The easiest way is to press up to get to the bottom. We're going to RREF. What are we going to RREF? We're going to RREF matrix A. Right, close the bracket, hit enter, and it did it. Right? If it's a big matrix like this where it's kind of off the screen, you can press the right arrow and it'll scroll to the right. But notice how we have the identity matrix right here, right? So A changed into the identity matrix. And so that means that what's on the right-hand side here is the inverse. And so I'm going to write this down right here. So we did RREF on the calculator, and we got this. Right, so A changed into the identity matrix, and that means what's over here ends up being the inverse. Right, so A changed into I, and I changed into the inverse. So since A reduced to the 3 by 3 identity matrix, this is the inverse. And you could double check if you want. I'm not going to do it here. I don't have enough space, but we could double check that A times A to inverse equals the identity matrix. It's a good double check, good practice of your multiplication skills if you want to double check that. Right, so when you multiply these two things on either side, you should get the identity matrix. Wonderful. All right, let me just show you one that doesn't work then. Hopefully this is not spoiling it for you that this one doesn't work. But let's try to find this inverse and just point out how we can tell it doesn't have one. So here's our matrix A. I'm going to put it in with the identity matrix. I'm going to white this out. Just stick it right in there with the identity matrix. There's I. We would row reduce it the exact same way using our calculator, just like I did in the last one. I'm not going to go into details on that, but I'll just write down the answer. When you row reduce, it ends up being this. All right, you can always stop. Like what I'm writing right here is meaningless because this didn't change into the identity matrix. But I will just write it down here in case you want to double check that. This is a good practice exercise and using the calculator if you want. But this is kind of the key thing, right? This did not reduce to the identity matrix. In the last one, A changed into I. Here, A did not change into I. And so that since A did not reduce to the identity matrix, A is not invertible. And as simple as that. Right, this works for any size matrix. You know, on tests and things, we won't go bigger than 3. It might be a bigger one in the homework where you have some more time to think about that. But yeah, I wouldn't expect a huge one in a test or anything like that. Okay. One last page in this section is just getting you to try this stuff yourself. And again, in person, I have people think about this either in groups, or a lot of times people just want to do it on their own, which is fine. I can't force you to do this in the remote setting, but it's a really good idea just to leave, even if you don't like take 20 minutes to write stuff down like I do in class, at least think them through. Get some scratch work written down on these problems. What can you did you learn something in this last section? Can you apply what we just learned a little bit? It's a really good test of your understanding. And if you, make small errors on this paper and then you watch me correct it, that actually is really helpful for learning. So please do think about these, right? So the first three here is finding the inverse of 2 by 2 matrices if it exists, right? Some of them will not exist, and so you should be able to think about that, right? These are all either 2 by 2s or some weird non-square one. So you can do these without using a calculator. Finding the inverse of this one, you're going to want to use a calculator, doing exactly what we just did on the last page. And then finally, notice how this system, this coefficient matrix is actually this one right here. And so the inverse you find right here, you can use to solve this system, again, just like we did a couple pages ago. Please do, this can really take you 10 minutes or so, 15 minutes if you take some time, just to look back at the section and see if this stuff makes some sense. Pause the video right now, give it a go. I am going to start going over it now. Okay, so this first one, this is a 3 by 2 matrix. It's not square. In order to talk about an inverse, we need to have a square matrix. Since it's not square, that means it's not invertible. All right, save yourself some work. There's no point in trying to find the inverse of that one. There isn't one. This one right here is invertible, and the inverse, we can just use the formula from this page, right? Switch A and D, B and C multiplied by -1, divide by 1 over AD minus BC. So we're going to use that formula to find this one. So we'll have 1 over AD minus BC, like that. And that's going to look like this. 1 over 35 minus 40, 7, 5, minus 4, minus 10. Which ends up being minus 7/5, 2 4/5, minus 1. And so again, you can use this one down on the one at the bottom of the page. The third one is not invertible, and I know that because of what it says on the first page here, right? So you need to do this 1 over AD minus BC, which is called the determinant. And what it says here is if that ends up being 0, that implies that A is not invertible. Well, in this particular one, 1 over AD minus BC is 1 over 24 minus 24, and so we get 1 over 0. And so since the determinant ended up being 0, we don't have an inverse. All right. On the 3 by 3 here, the inverse of this 3 by 3, we would want to use the technique on the last page, right? So we put this in a matrix with the identity matrix and row reduce. So there's A. I'm going to stick it in a matrix with I. Oh, by the way, I know I put this line down here. I'm not writing like an equal sign there. I'm just trying to separate the matrix from the identity matrix. I know it's probably obvious anyway, but I just wanted to clarify. I'm not solving an equation here. So I put A and the identity matrix in there and row reduce. I used my calculator to do this, and hopefully you did as well. And it turns out A does reduce to the identity matrix, right? So we do get A turning into I. And so that means whatever this is right here is the inverse. And so that turns out to be this. So this is the inverse right here. lastly, we can use this inverse right here to solve the system down at the bottom of the page. So we're going to solve this system, and I'm going to first do what I did in the section or the page 2 pages ago. I'm just going to write down the system in matrix form. So I'm going to write down the augmented matrix times the vector x1, x2, and it equals that constant matrix 1, negative 2. Right, so I'm just writing down sort of the AX equals B formula. And we know that if we multiplied the inverse on the left, this will cancel, and then this will end up being the solution. And again, we found the inverse of this right up here, so we don't even have to think too hard about that. So I'm going to multiply on the left by that thing we just found. And on both sides, of course, on the left. And these two things cancel. And then these two things ends up being the answer, right? So we end up with x1, x2 equals those two things multiplied, which is going to be, let me just do the details, it'll be minus 7/5 minus 4, 4/5 plus 2. Do that addition or subtraction, and we get this. Right? In other words, x1 is minus 27/5, x2 is 14/5. And we've done it with 2x2s a couple times solving the system, but again, it works for any size system and can actually be a really good way to solve systems in certain cases.